Continuing on with the Chem 112 lecture series, we're now going to be focusing on Chapter 11, which focuses on nuclear magnetic resonance spectroscopy, or NMR spectroscopy. NMR spectroscopy is probably one of the most versatile and useful methods to elucidate the structure of organic compounds. It can be used to figure out the connectivity of carbon-carbon and carbon-hydrogen bonds in a given molecule. So it's an extremely useful and widely applied method of structural characterization. So let's start by introducing NMR spectroscopy. So nuclear magnetic resonance spectroscopy, or NMR spectroscopy, is a widely used spectroscopic technique for structure determination in organic chemistry to map the carbon-hydrogen framework of organic molecules. NMR provides detailed information on the connectivity and relative stereochemistry of all atoms in your molecule. Here's an example proton NMR spectra. And from the proton NMR spectra, we can identify not only the identity of each proton found in our molecule, but the relative connectivity of each proton found in our molecule. So how does NMR work? Well, in order to collect an NMR spectra, you need to have a nucleus with an odd number of protons and/or an odd number of neutrons. In other words, a nucleus with net nuclear spin. NMR active nuclei include protons, the carbon-13, nitrogen-15, phosphorus-31, fluorine-19, xenon-129, and boron-11 nuclei. NMR active nuclei with a net nuclear spin have a net magnetic moment. So for example, if we think about a hydrogen nucleus, it will have a net magnetic moment, almost like thinking of a magnet. Now, initially, the magnetic moment of a given nucleus is not oriented in any specific direction. However, in the presence of an external magnetic field, each atom's magnetic spin orients in line with or opposed to the magnetic field. This generates two spin states that have different energies, and this is really important. So, initially, we just have our nuclei magnetic moment. They're oriented in any which direction. You then apply an external field, and as a result, you end up with two unique spin states with two unique energies. Your nucleus can either align its magnetic moment with the magnetic field, so this is aligned with the field, or its magnetic moment can be opposed to the external field. These two spin states each have a unique energy, and there's a clear and defined difference in energy between these spin states. So we have two spin states with different energy. Now, what this means is, for a given field strength, each atom, each nucleus, can absorb a specific frequency of radiation and requires a specific frequency of radiation to transition to the higher energy spin state. So if you apply and you allow your nucleus to absorb a defined frequency of light, you can promote your nucleus from the lower energy to the higher energy spin state. Now, why is this useful? Well, let's talk a little bit about field strength and this idea of chemical shift. So, a strong external magnetic field is needed for separation between spin state energies. The energy gap between spin states depends on the external magnetic field. So this difference in energy is proportional to the external field. And the reason why this is important is this difference in energy between spin states is proportional to the frequency of radiation required to promote and initiate a transition from the low energy to high energy spin state. The frequency of radiation required to transition a nucleus between spin states to the higher energy spin state, which is called placing the two nuclei in resonance, can be measured for each unique nucleus. So if you have two nuclei with different spin states of different energy, it requires a specific frequency of light, and your nucleus will absorb a specific frequency of light and in turn promote to the higher energy spin state. In other words, these two nuclei are now quote unquote in resonance. Because each nucleus absorbs a specific frequency of light based on the nucleus and based on the external magnetic field, we can differentiate nuclei based on the frequency of radiation that they absorb. So, how do we convert this into a more workable value? Well, this involves the chemical shift and this idea of the electronic environment. So in a magnetic field, the electron density surrounding each nuclei generates a local magnetic field that opposes the external magnetic field. For example, if you have a hydrogen atom and you place it in an external magnetic field, that hydrogen nucleus is surrounded by electrons. And those electrons in turn generate an induced field. What this means is this induced field that's generated by the electron density surrounding our nucleus results in shielding by reducing the effective magnetic field experienced by the nucleus. So for example, the net magnetic field experienced by the nucleus is the external magnetic field minus the induced field. So what that means is, for example, for a given hydrogen nucleus, because this gap in energy depends on the net magnetic field experienced by your nucleus, shielding reduces the effective magnetic field and thus influences the difference in energy between the two spin states. That in turn also influences the frequency of light that your nucleus absorbs to transition between those spin states. The chemical shift describes the frequency of radiation required to promote the nucleus to the higher energy spin state. And the key takeaway based on this idea of shielding is that different protons have different chemical shifts based on the electron density around that nucleus. If a nucleus has more electron density surrounding it, the induced field will be stronger, and that impacts the gap between the two spin states. If a nucleus has less electron density surrounding it, the induced field will be weaker, and as a result, the gap between the two spin states will widen and it will require more energy to transition between the spin states. So if there's anything I want you to take away from this theoretical overview of how NMR works, it's that different protons, different nuclei have different chemical shifts based on their chemical environment, based on the electron density surrounding that nucleus. So let's talk about the chemical shift. So as discussed, the chemical shift describes the frequency of radiation required to promote the nucleus to the higher energy spin state in part per million. So for example, if we have two spin states, in order to transition a nucleus between those specific spin states, it requires a specific frequency of light. And that is the chemical shift, the frequency of radiation required to promote the nucleus to the higher energy spin state. We can describe nuclei as shielded or deshielded. Shielded nuclei have a large amount of surrounding electron density, and shielded nuclei generally require less energy to undergo a spin flip and thus require lower frequency radiation for excitation. Shielded nuclei are on the right side of the NMR spectra, which is known as the upfield portion of the NMR spectra. Shielded nuclei on the right side of the NMR spectra, upfield, have low chemical shift values. In contrast, nuclei that are electron deficient are known as deshielded nuclei. Deshielded nuclei require more energy to undergo a spin flip and thus require higher frequency radiation for excitation. D-shielded nuclei are on the left side of the NMR spectra, known as downfield, at high chemical shift values. So as we can see, the left side of the NMR spectra contains protons that are downfield, D-shielded at large chemical shift values, while the right-hand side of the NMR spectra contains protons that are upfield, shielded, with low chemical shift values. Now, NMR spectra are often standardized to solvent or trimethylsilane, which is an additive that has a chemical shift of 0 part per million. It's a useful standard. One thing to note, we can collect NMR spectra, and we can also collect spectra for different nuclei for the same compound. For example, above, this is a proton NMR spectra, and we can just as easily collect a carbon-13 NMR spectra for the same compound. So NMR spectra can be collected for protons and carbon-13 nuclei in separate runs. The same principle of shielded versus deshielded nuclei applies in both cases. Deshielded nuclei with high chemical shift values are on the left. Shielded nuclei with low chemical shift values are on the right. Let's talk now about some general features of NMR spectra. The location and chemical shift of each signal indicates the electronic environment and the relative amount of electron density surrounding each proton. Different protons attached or adjacent to different atoms or different functional groups have unique chemical shift ranges. For example, a methyl proton has a chemical shift of around 0.8 part per million. By the same token, an alcohol proton has a chemical shift of somewhere around 3.0 to 4.0 part per million. So as you can see, depending on the chemical environment of a proton, it will have a unique chemical shift value. Another feature to pay attention to, in addition to the chemical shift, is the integration. The area under each signal, or the integration, indicates the number of protons generating the signal at that chemical shift. For example, an integration of 3 tells us that 3 hydrogens are generating that signal. An integration of 2 tells us 2 hydrogens are generating that signal. In addition to integration, the shape and splitting of each signal indicates the number and grouping of adjacent protons. For example, this peak appears as 1, 2, 3 lines, so we would call this a triplet. This adjacent peak appears as 4 lines, and it's called a quartet. The multiplicity and splitting of each peak tells us whether a pair of protons are adjacent, coupled, or non-adjacent, not coupled. Here's an example of an NMR spectra, and as you can see, we can differentiate and assign the identity of each proton in this spectra using the integration, the multiplicity, and the chemical shift. So for example, we're going to, throughout this chapter, take a look at different NMR spectra, use the chemical shift values for each peak, use the integration value for each peak, and use the multiplicity of each peak to differentiate and assign the identity of unique protons in unique compounds. So we're going to talk a lot about chemical shift, integration, and multiplicity throughout today's lecture. And in the end, we'll be able to draw the structure of organic molecules from the NMR spectra. Okay, let's now talk about chemical equivalence and unique signals. So, protons in the same chemical environment are equivalent and have the same chemical shift. If your proton has the same chemical environment, it's attached to the same type of carbon atom, then it will have the same chemical shift. We call protons in the same chemical environment and equivalent protons a special name. These are called homotopic protons. These are two hydrogen atoms that are in identical environments with the same NMR signal. A key test for homotopic protons is to replace the two suspected protons with an atom that we'll call X. If this gives identical molecules, these protons are equivalent. And the reason why this is important is equivalent protons give a single NMR signal. For example, these two protons are equivalent. The way that we can prove that is if we replace each proton sequentially with an atom that we call D, and we compare these two test compounds, these two test compounds are identical. And what that tells us is, what that allows us to conclude is that these two protons are chemically equivalent. Another test for chemically equivalent protons is that two protons are chemically equivalent if they're identical via an axis of plane or plane of symmetry. Further, chemically equivalent protons can be interchanged via rotation or reflection. For example, in ethane, these two sets of protons are equivalent, and we would see one signal for this entire set of protons. And we can see that by virtue of the fact that this molecule contains a clear mirror plane, and each of these hydrogens are interchangeable via rotation. So anytime there's a plane or axis of symmetry, you're going to start to see chemically equivalent protons. These protons are in the same chemical environment and thus are part of the same signal. Here's another example. Looking at acetylene, looking at these two protons are equivalent by virtue of a plane of symmetry. You can also show that via rotation, these two protons are equivalent via rotation. So these two protons are equivalent. And as a result, only one proton NMR signal is produced. So let's try to apply what we've learned now. And I'd like you to tell me how many unique proton NMR signals would you expect to see for the following compounds? I'll do the first one, you'll do the second one. So in this case, we have two sets of protons. So these two protons have unique chemical environments, so we'd expect to see two unique signals. Now, you may be asking, what about these protons on the other side of the molecule? Well, in this case, we can see that there is a clear plane of symmetry, and as such, these two methylene protons are equivalent. They're identical. And thus, we would see only two unique signals corresponding to these two unique sets of protons. So because there is a plane of symmetry, We only see two unique signals because we only have two sets of protons in a unique chemical environment. And why are they in a unique chemical environment? Their connectivity, what atoms are attached to each carbon that the protons are attached to, are different. With this example in mind, I'd like you to approach these next two examples, and I'd like you to tell me how many unique proton NMR signals would you expect to see in the following compounds? Okay, so looking at this first problem for cyclopentane, we can see that there are multiple planes of symmetry. And in fact, as we can note by these multiple planes of symmetry, all of these methylene protons are identical. They are interchangeable via rotation or reflection operation. You can prove this to yourself by if you mark one of these methylene carbons and I were to rotate this cyclopentane ring, you would not be able to tell the difference between this methylene carbon and the protons attached and this methylene carbon and protons attached. They are completely identical, completely interchangeable via rotation. And thus you would see one signal for all of the protons found in this molecule because all of the protons are chemically equivalent. Let's look at this next molecule. In this case, we have a clear set of axes of symmetry. And as such, when we think about these methyl groups, what we can see is these methyl groups are interchangeable via rotation or reflection across a plane of symmetry. And thus, all three of these methyl groups are equivalent. So we would see one signal for these methyl groups, and then a second signal for the methyl group that's attached to the oxygen because it has a unique chemical environment. So in total, we would see two signals for this compound. So again, it's always important to be vigilant and check for chemically equivalent protons. Check for axes and planes of symmetry. We're now going to talk about two other classes of proton. The first class of proton we're going to talk about are enantiotopic protons. As the name implies, these are protons that have an identical chemical environment, but when replaced, give a set of enantiomeric compounds. Enantiotopic protons are chemically equivalent as they are interchangeable via reflection. If we look at, for example, these two protons, now that we have methyl groups, what we can see is that if we replace each of these protons successively with a test group D, what we find is that this pair of test molecules are enantiomers. And as such, these two protons would be considered enantiotopic. These two protons in red and blue are enantiotopic protons. In practice, if you take a proton NMR in most cases, enantiotopic protons are chemically equivalent. However, enantiotopic protons are unique in that they can be distinguished using chiral solvents and reagents. So if we're taking a look at this molecule here, we can see that these two protons are enantiotopic. They are chemically equivalent. There's a clear mirror plane. But as we can see, if we replace these protons with a test group that I'm going to call X. What we see is after we replace each hydrogen with a test group X, we can see that these two test compounds are enantiomers. So enantiotopic protons, it's important to be able to recognize them, but when you take an NMR spectra, unless you're using a special solvent or special conditions, enantiotopic protons will appear like any other pair of chemically equivalent protons. The protons that you do need to be looking out for and being really careful with are diastereotopic protons. Diastereotopic protons are not chemically equivalent. Each proton has a unique signal. Diastereotopic protons are two protons that, when replaced, would generate a set of diastereoisomers. Diastereotopic protons are observed in some alkenes, chiral molecules, and cyclic molecules. The key signpost that you need to look out for diastereotopic protons is the presence of a stereocenter. Anytime you have a stereocenter in your molecule, that in turn can generate and lead to diastereotopic protons on adjacent atoms. To showcase this, if we take each of these protons in red and blue and replace them with a test atom D, we see that this pair of test molecules are diastereomers. They're diastereoisomers. And thus, these two protons are diastereotopic. And thus, these two protons would yield two unique signals because these are unique protons. Let's look at another example. If we have a cyclic molecule, here it's pretty easy to see. And the main test for that is just, let's say, and let's suppose, we replace this proton D with a test group X. As we can see very clearly, replacing a different proton with a different test group X generates a unique diastereoisomer. What that tells us is that protons D and C, these two protons, are diastereotopic. Which means these are unique protons. Now, what's something that's pretty funny about this molecule is it contains a plane of symmetry, and as a result, the two protons on each side of the ring are identical. So we have a pair of diastereotopic protons, and the protons on the other side of the ring are identical chemically equivalent protons. Generally, when you have these kinds of ring systems, what you will find is because you have a unique group on one face of the aromatic ring, what you will find is that each hydrogen on the same face and each hydrogen on the opposite face to that group in the ring will have a unique chemical environment, and as such will yield a unique signal. So diastereotopic protons are really common when you have these kinds of cyclic molecules containing a chiral center or a center that could become a chiral center. So because this methyl group is on one unique face of the ring, all the protons on the same face of that ring will have a unique chemical environment compared to the protons on the opposite face of the ring. Here's what this looks like in a 3D model view. You have your methyl group. The hydrogens that are on the same face of the ring as the methyl group are unique compared to the hydrogens on the opposite face of the methyl group, because these hydrogens on the bottom face are interacting with this hydrogen on the bottom face. As such, counting, we would expect to see 1, 2, 3, 4 unique signals. So we have 4 unique hydrogens and 4 signals. Again, always be on the lookout and double check for the presence of an axis or plane of symmetry. The last case of diastereotopic protons involve protons in an alkene. As we can see, proton A is cis to the chlorine atom, while proton B is trans. Proton C is unique because proton C has a unique environment. It's on a carbon attached to the chlorine versus protons A and B, which are on a carbon that's part of the alkene attached to another carbon. We can verify proton A and B are in fact diastereotopic because if we replace proton A with a group X versus replacing proton B with a group X, we see that we get a mixture of the cis and trans diastereomer, and as such, protons A and B in this molecule are diastereotopic. And as such, we will see 2 unique signals. 1 unique signal per each diastereotopic hydrogen. In total, we would see 1, 2, 3, a total of 3 unique protons, and thus we would see 3 signals. So, diastereotopic protons are very important to pay attention to. The most common place that you see diastereotopic protons are in alkenes, but you can also see it in molecules, be it cyclic or acyclic, containing a stereocenter or pseudo-stereocenter. So let's do some practice now. Let's try to identify some chemically unique protons. I'll do the first one, you'll do the second one. Looking at this molecule, we have a clear plane of symmetry. What that means is the protons on each side of the plane of symmetry are chemically equivalent. So what that means is these 2 protons here would be 1 signal, and these 2 protons here, as they're chemically equivalent, would be part of a second signal. We also have a third unique proton at the bottom of our molecule, and thus we would see a total of 3 unique NMR signals for this molecule. The reason why we only see 3 signals is because we have a pair and another pair of protons that are chemically equivalent by virtue of this clear axis and plane of symmetry. With that example in mind, I'd like you to take a look at these next 4 compounds, and I'd like you to tell me how many unique NMR signals would you expect to see for each of the following compounds. Okay, so let's take a look at the following molecule. In this case, this molecule contains a clear plane of symmetry. What that means is these methyl group protons are chemically equivalent. These 2 protons are equivalent. And thus we would see only 1 signal for each of these 2 methyl protons. So these methyl groups will all be as part of 1 signal corresponding to 6 hydrogens. We will see a second unique signal from this hydrogen because it's in a unique chemical environment, and a third signal from the alcohol proton because that is a proton in a unique chemical environment. So in total, this molecule would have a total of 3 signals, 3 chemically unique protons. Looking at this next case, this is propane. Propane contains a clear and very easy to see plane of symmetry. And what that means is these methyl protons are identical, and we would see only one signal for this set of 6 protons. We would see a second signal from these methylene protons. So in total, we would see 2 signals. For those wondering, why aren't the methyl and methylene protons equivalent? Well, they have different chemical environments. The protons on the methylene group are attached to a carbon that's attached to 2 carbons, while the methyl group protons are attached to carbon that's only attached to 1 carbon. So we have 2 unique signals because we have 2 sets of protons with unique chemical environments. The last case, this last molecule here, we have a pair of protons that are diastereotopic. These 2 protons are unique, and we would see a unique signal for each diastereotopic proton, a third unique signal for this hydrogen in a unique chemical environment, and a fourth signal for the methyl group proton, which again is in a unique chemical environment. To prove that those protons that we stated are diastereotopic, you can replace them with a group that we can call X. And as we can see, if we replace our supposed diastereotopic protons with a group X, we see that we get a pair of diastereomers. And that in turn tells us that these 2 protons are diastereotopic and they're chemically unique protons. Thus, for this molecule, we would expect to see a total of 4 signals. Let's do some additional practice now, and I'd like you to tell me, are the following protons chemically equivalent? So I'd like you to tackle each of these 3 examples, and I'd like you to tell me, are the following protons that I've drawn out chemically equivalent or not? So pause the video, work through this example, and then we'll discuss. So in this case, we have a stereocenter. And as a result, these 2 protons are diastereotopic. The proton on the same face to the methyl group will have an entirely different chemical environment versus the proton on the same face as the hydrogen. So these 2 protons are not equivalent because they are diastereotopic protons. Looking at this next molecule, this molecule contains a clear plane of symmetry, and these 2 protons have the same chemical environment, so these 2 protons are equivalent. These are identical protons. Looking at this last molecule here, we have another example where these 2 protons are diastereotopic. If you were to replace these protons with a group, you would get a mixture of cis and trans isomers. As you can see in this molecule, one proton is cis to the ethyl group, the other proton is trans to the ethyl group. So these protons are unique. Diastereotopic protons are not chemically equivalent. Okay, so we've gotten pretty good at identifying identical and unique protons, and we've gotten used to looking for and identifying axes and planes of symmetry. What we're now going to do is we're going to talk a little bit about the chemical shift. To this end, I have an appendix which contains some chemical shift values for you to reference. I would encourage you to have this table of chemical shift values available as we go through the next part of this lecture. As a general rule, proton signals range from 0 to 14 part per million, and electronegative atoms attached to adjacent carbons cause the proton to be shifted downfield. This explains why, for example, carboxylic acid and aldehyde protons are relatively downfield, as well as protons attached to carbons containing electron withdrawing groups, such as oxygen, fluorine, chlorine, bromine, and iodine. Now, to explain what's going on with the aromatic and alkene protons, we're going to have to discuss another topic, which we'll discuss momentarily. So here's a table of chemical shift values. I would encourage you to reference it throughout this next chapter discussion, so please have this page handy. In order to help us develop a qualitative model to estimate chemical shift, let's talk a little bit about chemical shift and inductive effects. Strong electron withdrawing groups de-shield adjacent protons. What that means is protons adjacent to stronger electron withdrawing groups exhibit a downfield chemical shift. So for example, if we exchange hydrogen with iodine, which is an electron withdrawing group, we see that our proton chemical shift is shifted downfield. As we increase the electron withdrawing group strength, we see that our chemical shift for the proton attached to the carbon containing that electron withdrawing group gets pushed further and further downfield. What that means is we can estimate chemical shift by thinking about the relative electronegativity and electron withdrawing group capability of each group. For example, if we wanted to estimate the chemical shift of the proton attached to a carbon attached to the alcohol, we'd estimate it to be somewhere between 3.1 and 4.3, as oxygen is more electronegative than chlorine, but less electronegative than fluorine. Looking at our table, this chemical shift value is around 3.2 to 3.8, which matches and fits into our qualitative model. The stronger the electron withdrawing group attached to a carbon, the more downfield the protons attached to that carbon will be shifted. In addition to the strength of the electron withdrawing group, increasing the number of electron withdrawing groups adjacent to a proton also increases the downfield chemical shift. For example, if you go from adding 1 chlorine to 2 chlorine atoms, your chemical shift increases from 3.1 to 5.3 part per million. If we add another chlorine atom and we're looking at chloroform, chloroform has a heavily downfield shifted proton at around 7.3 part per million. For example, this proton adjacent to our carboxylic acid, we would expect to be around 2.2. If we add a chlorine to that same carbon, we'd expect it to be downshifted anywhere from 4 to 5 part per million. The more electron withdrawing groups you add to your carbon, the farther downfield the protons attached to that carbon will be shifted. Now, it's important to note that inductive effects decrease with distance from the electron withdrawing group. For example, the protons directly attached to the carbon containing the electron withdrawing group are heavily downfield shifted. As you get farther and farther away from the electron withdrawing group, your chemical shift value gets further and further upfield, as the electron withdrawing group has less and less of an effect on its chemical shift. For example, diethyl ether, these protons directly attached to the carbon attached to the oxygen, have a chemical shift value somewhere around 3.5 to 4.5 part per million. By the same token, as you get farther away from your electron withdrawing group, these methyl group protons have a chemical shift of around 1.0 part per million. The farther you get from your electron withdrawing group, the less of an effect it has on chemical shift. For those curious as well, diethyl ether also contains a plane of symmetry. One other thing I'd like you to note is that increasing substitution generally results in a downfield chemical shift. As you go from a primary, secondary to tertiary carbon, your chemical shift gets shifted, the proton gets shifted further and further downfield from around 0.9 part per million to 1.2 part per million for secondary carbon protons, all the way to 1.7 part per million for tertiary carbon protons. So the more carbons you have attached, the greater your substitution, the farther downfield your proton becomes. Let's talk about two phenomena that impact chemical shift. The first of which is this idea of anisotropic effects. So when placed in a magnetic field, pi bonds, such as those found in alkenes and aromatic rings, generate an induced magnetic field as a result of the circulating pi electrons. This induced magnetic field causes protons attached to pi bonds and aromatic rings to be shifted downfield. So if you have an external field, what happens is your pi bonds electrons circulate and generate an induced field, which in turn means that the protons attached to the aromatic ring are shifted downfield. This explains why your aryl protons are so far downfield at 7 to 8 part per million, and your alkene protons are also downfield at 4.5 to 6.5 part per million. Anytime you have a pi bond, those pi bond electrons will circulate and generate an induced magnetic field that results in the protons on the outside of the pi bond or pi system being shifted downfield. One other side effect that it's important to note, but it occurs in a pretty unique class of compounds, which are large aromatic rings. In large aromatic rings, protons in the center of the ring are shifted upfield. So you have your induced field. The protons on the outside of the ring are shifted downfield, while the protons on the inside of the ring are shifted upfield. And this is a pretty big difference. The outer hydrogens appear around 7 to 9 part per million, while these inner hydrogens appear around 1.8 part per million. So again, part of the reason why aryl and vinyl protons are downfield is as a result of anisotropic effects. This induced field shifting those vinyl and aryl protons downfield. One other effect that can cause problems in terms of observable chemical shift values is hydrogen bonding. So protons capable of participating in hydrogen bonds, such as alcohol, amine, and carboxylic acid protons, often appear broad. Protons participating in hydrogen bonding or hydrogen exchange can be detected by treating your sample with D2O, which exchanges, for example, the oxygen-hydrogen bond with an oxygen-deuterium bond, which does not appear in the proton NMR spectra. So for example, if you take a phenol and you treat it with D2O, that exchanges the oxygen-hydrogen for an oxygen-deuterium bond. In other words, if you treat with D2O, the oxygen-hydrogen HNMR signal disappears because deuterium is not detected in a proton NMR spectra. So what this means is we can detect hydrogen bonding groups, by using this deuterium wash test. Here's an example of this test where we have this phenol proton. As you can see, this phenol proton appears as a quite broad peak. After treatment with D2O, as we can see, the peak disappears. What this tells us is that this oxygen-hydrogen peak is participating in hydrogen bond, and it's labile for deuterium exchange. So we can detect and verify the presence of these hydrogen bonding groups by treating our molecule with a D2O wash and observing as that peak corresponding to the oxygen-hydrogen or nitrogen-hydrogen bond disappears after deuterium exchange. Okay, let's now do some practice. So I'd like you to practice now and predict the chemical shift of each chemically unique set of protons in the following molecules. And I'd like you to tell me how many signals would you observe for the following molecule. I want to give you a warning for this second compound. This is a stereocenter, and you're going to need to be wary of that when you think about how many unique signals you would expect to see in this compound. So pause the video, work through this example, and then we'll discuss. Okay, so looking at this first molecule, immediately there is a clear plane of symmetry. Let's now go through each unique set of protons and let's list their chemical shift. So first, looking at proton A, we have 3 hydrogens, and since we have a proton adjacent to a carbonyl, we'd expect a chemical shift around 2 part per million. The next set of protons are these methylene protons that I'll call HB. We have 2 hydrogens and we have a chemical shift value of 2.2 part per million. I indicated these protons as being further downfield by virtue of the fact that this carbon is secondary rather than primary. Next, we have the proton that's attached to this carbon. This proton appears Hc as a 1 hydrogen signal with a chemical shift of around 1.8 part per million because it is attached to a tertiary carbon. Finally, these 2 methyl group protons are chemically equivalent and would appear as 1 signal corresponding to 6 hydrogens and a chemical shift of 0.8 part per million. Okay, so we've identified each chemically unique proton in this molecule and indicated its chemical shift value. Now, looking at the following molecule, because it contains a stereocenter, we run into a huge issue where we have multiple diastereotopic protons. In this case, we have a set of 2 diastereotopic protons in our chain. In addition, we also have a pair of diastereotopic protons on the alkene. So in total, we would expect to see 1, 2, 3, 4, 5, 6, 7, 8, 9 signals because we have 9 unique protons. With that said, a lot of these protons, although they are unique, will have very similar chemical shift values. For example, these 2 vinyl protons will appear around 5.0 part per million, while this vinyl proton will appear around 5.5 part per million. The allylic protons even though they are unique, will both appear in a general chemical shift range of around 2.2 to 2.5 part per million. That's the typical range for the allylic proton. I indicated them closer to 2.5 because there are adjacent electron withdrawing groups. The hydrogen, the proton adjacent to the carbon attached to the alcohol, would have a chemical shift around 4.0, while the OH proton would have a chemical shift of around 1 to 5 part per million. I'd estimate it to be around 3.0 part per million. Finally, these two protons attached to our carbon, attached to the chlorine, these alkyl halide-like protons, we'd expect to have a chemical shift of around 3.2 to 3.5 part per million. So although we have multiple chemically unique diastereotopic protons, many of these diastereotopic protons will appear in very close chemical shift ranges. The main way that you often see diastereotopic protons differentiated is by virtue of the fact many of these diastereotopic protons will have unique splitting patterns, and in some cases, there's enough of a differentiation in their chemical environment that you see minor differentiation and separation between the diastereotopic proton peaks. Okay, so we've done a pretty good job at assigning and predicting the chemical shift of each peak in the proton NMR spectra for a range of different compounds. Let's do another example problem focusing on peak assignment. For here, I'd like you to assign each peak in the following NMR spectra to each proton in the given structure. And I've given you the integration as well, which tells you the number of protons generating that peak signal. So let's pause the video, work through this example, and then we'll discuss momentarily. Okay, so first and foremost, we have a clear plane of symmetry dividing the molecule. We have 1, 2, 3. Let's use a different color for that. 3, 4 unique protons. This CH3 group at around 2 part per million. This matches a benzylic proton, so I'll label this as proton A. The broad peak of around 5 part per million matches the alcohol proton, which I'll label as proton D. The aryl protons are hard to differentiate at this time. In terms of the actual assignment, these two peaks correspond to the two aryl protons. The protons labeled in black are actually going to be the farther downfield protons, while the protons labeled in blue are going to be the more upfield protons. For those curious why that is, it has to do with how electron density can be distributed in the ring. And in this case, if we look via resonance, what we can see is we can push a lot of electron density onto our alpha positions. So these alpha positions are more shielded than would be expected. While proton B in the meta position does not experience this effect, and as a result, proton B is farther downfield. You won't be asked to make this kind of subtle distinction for aryl systems. The key point that I want to drive home is that we can use our chemical shift values noting the fact that aryl protons have a chemical shift around 7.0. The alcohol protons has a chemical shift around 1 to 5 part per million, while benzyl and allylic protons have a chemical shift of around 2.0 part per million. So we can use chemical shift along with integration to assign the identity of each peak and determine the protons responsible for each peak in a proton NMR spectra. Let's keep going now and let's talk a little bit now about integration. So the relative intensity of a signal, or the integrated area, is proportional to the number of protons. The integration gives the ratio of chemically unique protons for each signal. The reason why I say ratio is because in cases where sets of protons are chemically equivalent, the integration will yield a ratio rather than the absolute number of protons generating the signal. For example, the following ketone contains a clear plane of symmetry. And as such, we have a pair of chemically equivalent protons. So this would be a 4-hydrogen signal, and a second pair of chemically equivalent protons that would be part of a 6-hydrogen signal. As a result, what we observe in the integration is a 2 to 3 ratio of protons when the actual ratio is 4 to 6. So, key thing to keep in mind, the integration is proportional to the number of protons, and the integration gives you the ratio of protons for each peak in your spectra. Let's try to apply this, and let's talk a little bit about predicting chemical shift and integration. Let's try to predict the chemical shift and integration for each chemically unique set of protons in the following molecules. And I'd like you to tell me how many signals would you observe for the following molecules. So pause the video, work through these 2 examples, and then we'll discuss. So in this case, we have a clear set of axes of symmetry. And as a result, these methyl group protons are all equivalent. So these methyl group protons would appear as one signal with 9 hydrogens and a chemical shift of around 0.8 part per million. By comparison, the protons adjacent to the carbonyl group would appear as a 3-hydrogen signal with a chemical shift value of around 2.2 part per million. In practice, you'd see a 3 to 1 integration ratio. What that means is, if you just took a look at the NMR spectra, you would see one large peak corresponding to the 9-hydrogen peak, and a smaller peak corresponding to the 3-hydrogen peak. The ratio would be 3 to 1 in terms of integrated peak height. Looking at this next example, diethyl ether, again, there's a clear plane of symmetry. And as such, we have one set of protons, which would be a 4-hydrogen signal. These are attached to a carbon next to oxygen, so we'd expect a chemical shift value of around 4.0 part per million. And then we have another set of equivalent protons, which are these methyl group protons, which would be a 6-hydrogen signal with a chemical shift value of around 1.0 part per million. This gives us an actual ratio of 3 hydrogens to 2 hydrogens. So if we took an NMR spectra, we would see one peak around 1.0, and then we would see a second. Sorry, I need to draw that as a triplet, and I need to draw that taller. So let's draw the peak around 1.0. This would be a triplet. And then we have a peak around 4.0 that would be a quartet with an integration for 4 hydrogens. For those wondering why I drew these peaks as a set of peaks, that has to do with multiplicity and splitting, which we'll talk about momentarily. Based on the integration, we'd expect to see a 3 to 2 ratio of peaks integration. So as you can see, we're slowly developing the tools to predict each part of a compound's NMR spectra, including both the chemical shift and the integration of each peak. Let's talk now and let's do another practice example regarding integration and equivalent protons. So what I'd like for you to do is to take a look at the following compound and the following NMR spectra, and I'd like you to assign each proton in the following structure to each peak in the NMR spectra. So in this case, I'd like you to use the tools of integration along with chemical shift to assign each proton in the following structure to each peak in the NMR spectra. So pause the video, work through this example, and then we'll discuss. So first and foremost, we have these methyl protons. These protons would appear as a 3 hydrogen signal with a chemical shift of around 2.0. That peak, which has an integration of 3 that shows up around 2.0, corresponds to the following peak, which matches these protons. Looking at the next peak, this methylene group, which I'll label HB, would be a 2 hydrogen signal with a chemical shift that's much more downfield than usual, somewhere around, I'd say, 3 to 4 part per million. In this case, that signal would correspond to the following peak. One thing that's also important to note, this peak is a singlet and not split. Looking at this next methylene group, this is a carbon adjacent to an oxygen atom, so it's highly downfield shifted at around 4.0 to 4.5, and we'd expect to see a 2 hydrogen signal, and we'd expect it to be a triplet. That matches, this proton group C matches the following peak, and the integration matches as well. The last peak, which corresponds to these methyl group protons, would be the most upfield, around 1.0 part per million, which corresponds to the following peak. One thing I'd like you to note is that protons C and D are coupled and they split one another. So the splitting pattern indicates that protons C and D are adjacent to one another and coupled to one another. So for this example, you can just use integration and chemical shift to assign the peak identity for each proton found in this compound. But if you add in multiplicity, you can get further evidence to support your peak assignments. Now, what is multiplicity? We'll actually be talking about that momentarily. For now, if you just think about the integration and chemical shift, you can assign the identity of each peak and each proton responsible for each peak in this structure. Let's do another example. Here we're asked to assign each proton in the following structure to each peak in the NMR spectra. And this time, this is where the ratio and relative ratio associated with integration comes into play. As you can see, the integration values do not directly match the number of protons that we have. So, take a few moments to work through this example. Think a little bit about the chemical shift value. Think a little bit about the broadness and shape of each peak, and then we'll discuss this example momentarily. One thing that I would like to flag for you to be wary of is I'm going to tell you right now that this peak integration is non-standard, and it has to do a little bit with the type of peak that we are looking at. So pause the video, work through this example, try to use the chemical shift and integration values to assign the identity of each peak, and then we'll discuss momentarily. So one thing to keep in mind is that this peak is very broad. So I'm going to label this proton as the amine proton. OH, NH, and carboxylic acid protons, anything that hydrogen bonds leads to broad peaks with often irregular integration. So in this case, the actual integration value and the actual integration ratio will be closer to 2. But because this peak is a hydrogen bonding peak, you'll usually see some irregularities where the integration is not quite what it should be. Nonetheless, we can still use integration for our other peaks to differentiate these other peaks. The protons adjacent to the amine, this molecule contains a clear axis of symmetry. So these two protons would appear as a single signal, which would be a 4-hydrogen signal. By the same token, as well, these two methylene protons would appear as a single 2-hydrogen signal. As we can see based on integration, the methylene protons would be here, and the protons attached to the amine would be here, just based on integration. This also makes sense from the perspective of chemical shift. The protons adjacent to the amine would be around 2 to 3 part per million, while these methylene protons would have a chemical shift somewhere around 1 to 2 part per million. The amine protons are a bit of a wild card in that you'd see a broad peak anywhere from 1 to 4 part per million, and in this case it's closer to 1. The way you can tell that this is an amine peak is if you look at this peak shape, it's a very broad peak compared to the other peaks, and it has no splitting. So anytime you see these sorts of broad singlets, and anytime you see a sort of weird integration, that's a sign that you have a hydrogen bonding group. So as you can see, we can use a combination of chemical shift and integration to differentiate and assign the identity of peaks in our structure. Let's now talk a little bit about multiplicity and spin-spin splitting in proton NMR spectra. So when a proton is adjacent to other protons, we observe multiple absorbances for that proton. In other words, that proton is split. This splitting pattern allows us to determine the relationship and position of adjacent protons in our molecule. Now, why does this occur? Well, spin-spin splitting is the result of the coupling between the spins of protons on adjacent atoms. In a magnetic field, each hydrogen nucleus generates a magnetic field. and each hydrogen nuclei's spin can be aligned or opposed to the magnetic field. Thus, for n adjacent protons, there are n plus 1 spin orientations and unique fields. Thus, an adjacent proton would experience n plus 1 unique magnetic fields, where n is the number of adjacent coupled protons. In other words, an adjacent proton signal would be split into n plus 1 peaks. For example, let's take a look at this bromoethane compound. As we see, if we look at this CH2 group, there are 3 hydrogens adjacent. N is equal to 3, so n plus 1 would be equal to 4. As you can see, this CH2 group proton experiences 1, 2, 3, 4 unique magnetic field environments, and thus we see 1, 2, 3, 4 unique peaks. This proton signal is split into 4 unique peaks that we call a quartet. Taking a look at our methyl group, as you can see, it has 2 hydrogens adjacent. And as a result, n is equal to 2, so n plus 1 would be 3. So we see this methyl proton is subject to 3 unique chemical environments, and thus we see, 3 unique magnetic environments, and thus we see 3 unique peaks. This would be known as a triplet, which we abbreviate as T. Let's make sure that we really understand this splitting rule, and let's take a look at the following compound where we have a single proton adjacent to 2 other protons. So first and foremost, looking at proton A, we see that there are 2 adjacent protons, and as a result, we would see 3 unique magnetic environments. So for HA, it would be split into 1, 2, 3 unique magnetic environments, and thus we would expect to see 3 peak signals. So we would expect to see a triplet. By the same token, if we take a look at proton B, it has 1 adjacent proton, n plus 1 is 2, so proton B we would expect to be split into 2 proton signals on account of the 2 unique magnetic environments. And thus we would expect to see 1, 2 peaks, which would correspond to a doublet. One thing that's also important to note is the separation of peaks, known as the coupling constant, is identical for coupled protons. So as you can see, we can tell that these 2 protons are adjacent and coupled because they have the same coupling constant of 7 Hertz. This is why I was very careful to draw out the separation between my split peaks to be identical. If these 2 protons are adjacent and coupled, they'll have the same coupling constant, the same spacing between peaks. Let's delve into a little bit of detail regarding multiplicity. So multiplicity is the number of peaks in a signal. If we see a single peak, it's a singlet, 2 peaks doublet, 3 peaks triplet, 4 peaks quartet, 5 peaks quintet, 6 peaks sextet, 7 peaks septet, and so forth. Spin-spin splitting occurs if there are chemically unique protons on adjacent atoms. It's important to be very clear that chemically equivalent protons do not split each other. So for example, if we look at chloromethane, these 3 CH protons are chemically equivalent, so they do not split each other. By the same token, in 1,2-dichloroethane, these two protons are equivalent, and thus no splitting occurs. We'd see one peak corresponding to an integration of 4 hydrogens. We can see a pretty striking example of this in cyclopentane, where all of these methylene protons, all of these CH2 protons are equivalent. So what we would see is one single peak corresponding to a 10 hydrogen integration that is a singlet. No splitting. Chemically equivalent protons do not split each other. This is a very important idea. One other thing to note is that protons attached to the same atom do not split each other unless they're diastereotopic. This makes sense because these protons that are attached to the same atom are typically equivalent. The only exception to this rule concerns diastereotopic protons. And because diastereotopic protons are in turn unique protons, they do in fact split one another. So the key place where this comes up is when you're dealing with alkenes or when you're dealing with molecules containing a stereocenter. So these are some exceptions. So again, the key thing to keep in mind, chemically equivalent protons do not split each other. One other rule to keep in mind is that protons on adjacent atoms can split one another. Protons separated by more than 3 sigma bonds usually do not split each other, with some exceptions that are discussed in more advanced organic chemistry courses. So generally, protons must be adjacent in order for splitting to be observed. Let's talk a little bit and let's do some practice now regarding multiplicity and spin-spin splitting. So here I'd like you to determine the multiplicity of each signal for the following compounds, proton NMR, and I'd like you to predict the integration and chemical shift of each peak. So pause the video, work through this example, and then we'll discuss. So let's take a look at this compound. This compound contains multiple planes of symmetry, and as such, all of these methyl group protons are chemically equivalent. So for these protons, they are adjacent to one hydrogen. So we'd expect to see a 9 hydrogen peak. N is equal to 1, so N plus 1 is 2. So we'd expect to see a doublet with a chemical shift value corresponding to about 0.9 part per million. In comparison, this proton here, which we'll label proton B, would integrate for one hydrogen. N is equal to 9, so N plus 1 is 10. So it would be a decet. So it would be split into 10 little subpeaks. And we'd expect a chemical shift value of around 1.8 part per million. So here's what the spectra would look like. So this is 2, this is 1. We'd see a very large doublet corresponding to 9 hydrogens at around 0.9, and 4, 5, 6, 7, 8, 9, 10. Corresponding to this one hydrogen peak at around 2.0. Once you get to multiplicities above 8 or 9, it starts to look like a multiplet blob that's hard to resolve using most low resolution NMR instruments. Let's take a look at this next compound. In this case, we have a methylene group that I'll label as proton A. We have another methylene group that I'll label as protons B, and a third set of protons on the methyl group that I'll label as proton C. Looking at proton group A, we'd expect them to integrate for 2 hydrogens, have a chemical shift value somewhere around 3.5 part per million. And because n is equal to 2, n plus 1 is equal to 3, so we'd expect it to be a triplet. Proton group C, we'd expect them to integrate for 3 hydrogens. Their chemical shift value is going to be around 1.0 part per million. N is equal to 2, n plus 1 is 3, so we'd expect a triplet. Now, for proton group B, this is where things get a little bit interesting. They would integrate for 2 hydrogens. The chemical shift value would be somewhere around 1.2 part per million. In this case, n is equal to 5, so you'd expect to see n plus 1 equal to 6. So you'd see 6 little subpeaks. In reality, this compound would be a triplet of quartets. There'd be primary and secondary splitting and would often cause it to look like a multiplet. We'll talk a little bit about what happens when you have multiple unique groups splitting your proton signal momentarily. In practice, if you use a low resolution instrument, it's often difficult to tease out some of these more complex splitting patterns. Let's do another practice example. In this case, we have a compound structure in an NMR spectra, and we're asked to assign each peak in the following proton NMR spectra to each proton in the provided structure. So pause the video, work through this example, and we'll discuss momentarily. So in this case, first and foremost, we can see that there is a plane of symmetry. So these 2 methyl group protons will be one signal that I'll call proton A. We have a hydrogen attached to the carbon attached to the oxygen that I'll label as proton B. And this methyl group adjacent to the carbonyl we'll label as proton C. Proton A, we'd expect it to integrate for 6 hydrogens, have a chemical shift of around 1.0, and we'd expect, because n plus 1 is 2, that it would be a doublet. That corresponds to the following peak. Proton B, we expect to integrate for 1 hydrogen, have a chemical shift of around 4.5 part per million, and n plus 1 in this case would be 6 plus 1, which would be 7, which would be a septet. Proton B matches the following peak. We can also tell that protons A and B are adjacent because they have the same coupling constant of 6.8 Hertz. The last proton, proton C, would just be a 3 hydrogen singlet with a chemical shift of around 2.0, which matches the following peak. So we're able to use both the multiplicity, integration, and chemical shift to assign each proton in the structure to a unique peak in the NMR spectra. Let's talk a little bit now about coupling constants and spin-spin splitting. The exact protons coupled to a proton signal can be identified using the coupling constant. Coupling constants also provide information on the relationship between coupled protons. For example, two generic alkyl protons have a coupling constant of around 6 to 8 hertz. Trans vinylic protons have a coupling constant of 11 to 18, while cis vinylic protons have a coupling constant of 6 to 15. Geminal vinylic protons have a coupling constant of 0 to 5, and this can be hard to see on low resolution instruments. So you may not always see the geminal vinylic proton coupling. The coupling constant can also be used to identify alkene stereochemistry and the position of substituents in an aromatic ring. For example, ortho groups have a coupling constant of 6 to 10. By comparison, meta protons have a coupling constant of 0 to 4. One other coupling constant that does pop up is the aldehyde coupling constant, where protons can couple to the aldehyde proton with a coupling constant of 2 to 3. Now, as we alluded to in the earlier example, when a proton is adjacent to multiple chemically unique protons, it is split by both protons, each with a unique coupling constant that we'll call J1 and J2. This yields a multiplet that may be resolved. So for example, let's take a look at proton that I'll label HB. It's adjacent to a proton A and proton C. Now, in terms of coupling, the coupling between protons A and B, this is a trans vinylic proton coupling, so it's going to be about 12 hertz. This is a trans vinylic coupling. Next, we have a coupling between protons B and C, which has a coupling constant around 6 hertz. Now, because this proton is adjacent to two chemically unique protons, it's split by each proton successively. So in the first case, we are split by proton A with a coupling constant of 12 hertz. From there, our peak is further split by proton C, where this coupling constant is 6 hertz. This in turn leads to a multiplet that we call a doublet of doublets. It's important to note the proton with the larger coupling constant splits first, followed by the proton with the smaller coupling constant. So we're able to not only determine the connectivity and adjacency of protons, we can also identify the relationship between two protons using the coupling constant. Let's talk now about complex splitting patterns. So if the instrument resolution is sufficient, complex splitting patterns can be resolved. The splitting pattern for multiplets is reported using the primary and secondary splitting. For example, proton C can be reported as a doublet of doublets with a coupling constant of 1.5 and 17.4. The larger coupling constant of 17.4 is listed first, followed by the smaller coupling constant. As we can see, we can differentiate these protons A, B, and C based on their coupling constant and splitting. So let's talk a little bit about that. So looking at proton C, which is right here, proton A is right here, and proton B is right here. Thinking about the coupling constant between A and C, that's a trans vinylic coupling. That's going to be about 17 hertz. While the coupling constant and the coupling value between B and C is a geminal coupling, and that's going to be about 2 hertz. We can see that in the peak splitting pattern, where we see a large initial splitting from the first coupling constant, followed by a smaller splitting by the smaller hydrogen Bc coupling constant of 1.5 hertz. So, by looking at the splitting pattern for a peak, we can differentiate each proton. Let's look at proton B now. The coupling constant between protons B and C is still 2 hertz. What changes now is that the coupling between protons A and C, this is a cis vanillic coupling, and so it's going to be around 10 hertz. So as you can see, this time we have a 10 hertz coupling constant for proton B versus a 17 hertz. And we can see that by the fact in proton B, the peaks are that when they're split, the peaks are closer together. Do you see how in proton C, because it has a larger coupling constant, the peaks are farther apart? That's how we can differentiate protons B and C. By virtue of the fact that proton B is a cis coupling pattern with proton A, while proton C is a trans coupling pattern. Proton A is most easily distinguished because it has both an AC, which is a trans coupling constant with coupling between protons A and C, which has a coupling constant of 17 hertz, and a cis coupling with proton B, which is 10 hertz. And we can see that based on the spacing and separation between our peaks. So in this case, we have our initial separation, our initial splitting of 17 hertz, followed by a secondary splitting of 10 hertz. So by analyzing the splitting pattern and coupling constants, we can in turn differentiate these 3 vinyl protons. Now, this doesn't always work. In some cases, in fact, in many cases, peaks overlap or cannot be resolved, so the peak is reported as a multiplet. An example of that we looked at previously is in phenol, where one major complication that I'd also have to bring up with regards to splitting is that alcohols, amines, and carboxylic acid protons are broad due to hydrogen exchange. Thus, the OH proton does not have a lot of observable splitting patterns. Anytime you have a proton that's undergoing exchange due to hydrogen bonding, it'll often exist as a broad singlet. Okay, let's now try to apply what we've learned with regards to complex splitting patterns. I'd like you to take a look at the following molecule in the following NMR spectra, and I'd like to assign each peak in the following NMR spectra to each proton. And I'd like you to tell me, based on the coupling constants, is the alkene in this structure cis or trans? And I'd also like you to tell me, is the alkene geminal substituted? So what is the exact substitution pattern of the alkene? Is it cis with a coupling constant of around 6 to 10? Is it a trans alkene where the proton coupling constant is 10 to 17? Or is it a geminal substituted alkene with a proton coupling constant of 0 to 5 hertz? So pause the video, work through this example, and then we will discuss momentarily. So first and foremost, let's assign the identity of each peak. I'll label the proton adjacent to the carbonyl proton A. This will be a proton with a chemical shift of around 2.0 as a singlet. That's this proton. The proton adjacent to this methyl group, sorry, the proton on this methyl group that's adjacent and attached to this oxygen atom will be labeled as proton B. This would have a chemical shift somewhere around 3.5 to 4.0. That's this proton here. The next part concerns our two vinylic protons that I'll label as proton C and proton D. Proton C is closer to the stronger electron withdrawing group, while proton D is closer to the weaker electron withdrawing group. From here, let's now take a look at the coupling constant. You can estimate the coupling constant by looking at the splitting or separation of each peak. So in this case, we have a peak splitting of approximately 0.2 part per million. And given that you're going to need another piece of information to convert this into a formal coupling constant, you'll need the instrument, you'll need to have the Hertz value of the instrument. So NMR instruments can be 60, 80, 100, 400, 600 megahertz. This spectra itself was collected on what I believe to be a 100 megahertz instrument. And so this gives us an estimated coupling constant value of around 17 to 20 part per million. As we can see, the separation between our peaks is quite large. So this suggests to me that we have the trans alkene. So anytime you see alkene protons and you have a very large separation between your peaks, that is a signpost that you are most likely dealing with a transalkene, because transalkene protons have a coupling constant of 17. Cisalkene protons have a coupling constant closer to 6. Okay, so as you can see, we can use the coupling constant in order to estimate and predict and assign whether an R alkene is a cis, trans, or geminal substituted alkene.